Hi, I'm Ahmed Abdelreheem, and I'm going to discuss our recent project 3D ReferIt3DTransformer, fine-grained object identification in real-world scenes using natural language. In this work, we study fine-grained 3D object identification in real-world scenes described by a textual query. The task aims to discriminatively understand an instance of a particular 3D object described by natural language among other instances of 3D objects appearing in a visual scene. The input is an object segmented point cloud 3D scene and a textual query which we call it an utterance, and the output should be the target object described by this utterance. We introduced the 3D ref transformer, a transformer-based neural network that identifies 3D objects described by linguistic utterances in real-world scenes. First, we encode each modality using a separate transformer encoder, where we allow tokens within the same modality to attend to each other. Then, we further encode all the tokens coming from both modalities through a multimodal transformer, where each token is allowed to self-attend on other tokens either from the same or different modalities. To help distinguish the target object from its distractors, we compute a scaled cosine distance between each object and the mean of all language tokens. Compared to the state-of-the-art models, our 3D ref transformer net offers two key advantages. First, it's an end-to-end transformer model that operates both on language and 3D visual objects. Second, it has a natural ability to ground textual terms in the query to the learning representation of 3D objects in the scene. We further introduce an auxiliary loss on predicting the spatial relationship between pairs of objects. This loss guides the object transformer to understand the spatial relationships between objects present in the scene. We incorporate contrastive learning signals during training. Contrastive learning losses help the model better separate between similar language utterances and objects. For example, a positive utterance and target object pairs should be away from other negative utterance and distractor object pairs. In target object to negative utterance loss, the similarity between the positive utterance and the target object should be the maximum, and at the same time the similarity between the target object to the sampled negative utterances in the mini-batch should be lower. We show in our experiments that our model improves the performance on the current benchmarks by a significant margin. By incorporating the contrastive loss, the performance in the hard context improved much. We investigate the effect of incorporating different positional embeddings to object point cloud features for the object transformer. We want to see how much PointNet++ can convey such positional information. We try first not to include any extra positional information. Second, we encode each object's bounding box center and dimensions, and then sum it up with the PointNet++ feature. Third, we encode the pairwise object distances and then sum them with the pairwise attention weights in the object transformer's self-attention layers. We show here the results of a variant of our model. The results suggest that PointNet++ conveys the positional information, however, adding explicitly absolute positional embeddings improves the performance in the hard contexts. Here are some qualitative examples based on our best performing model. Thank you for watching.